Hey students, this will be a good chance to self-grade and get an idea of how you did while I'm busily grading these, and it'll also give you a chance to see what your mistakes are, and hopefully they're still fresh in your mind, and you'll be kind of curious to know, what you did right, as well as, kind of correct what you did wrong, and so learn from those mistakes. Anyway, so let's jump into the exam. Here's the first question. It's got these two parts, and we got a ray coming down here. It says this ray A, traveling straight down, hits mirror 1, reflects off, hits then mirror 2, and then bounces off of it and exits as ray D. How much has the original A deviated from its original path? That is, if you extend this ray down and then the new ray D out to here, it's really saying, what's this angle here, theta? How much has it bent? How much has it twisted here? And you can see here that this is going to be a law of reflection. And if you're looking ahead and you already did the exam, you'll see that the other one is the law of refraction. And so I'll kind of draw the two mirrors here. And the first ray comes in and, of course, hits the mirror, and it's measured from the normal. Now, they show in the diagram here that this is 115 degrees. If I drew a vertical line, of course, this would be 90, and that leaves 25 for this little piece. And I'm going to take that to my advantage and then call that a 25, which means the angle of incidence is 65. And so as the ray bounces off, and I made that a little too tight for clear vision, this would be 65, because that's what, we mean here by the law of reflection. And that means this angle in here is 25, not to be confused with the 25 that I labeled there. And so then if we draw this triangle here with this one at 115 and this at 25, and so 115 plus 25 is 140. That leaves 40 degrees left because the sum of all three angles of a triangle is 180 degrees. And so we've got a little 40 tucked under there, which means 50 degrees is the angle of incidence for mirror 2. And then because of the law of reflection, a second time, so just like these were both 65, these are both 50. This angle would be 50, which would make that angle there 40. Now, there's a couple ways we might do this problem. Maybe the first one is to ask, how much has this original beam twisted? It was going straight down, and now it's going this way. And so you can see that the twist angle, if I kind of extend this ray down, this twist angle would be the, these three added together, the 65, the 65, and then this twist. Let me call that angle or twist bend angle number 1. I'll just call it theta 1, not to be confused with the theta in the diagram. But one way I might approach this is say, okay, so this would be 180 and then minus 2 times 65. And 65 twice is what, 130? And so that leaves 50 degrees for my first twist. And so as this ray comes, if I extend it out by the same logic, how much did it twist there? I'll call it twist or bend. Probably better to call it deviation, number 2, would be where it was going. So 180 minus, again, these two reflected angles. So 2 times 50, which leaves me with 80. So the total twist should be 130. Now, I suppose that should be the same number if we kind of draw this ray back And that's kind of how it is shown in this diagram, theta. And so I'm looking for theta. And maybe the way to do that is to draw a horizontal line here, because that horizontal will match this horizontal mirror here. And let's see, what am I looking for? Oh, I guess this angle here would be 40, and that would correspond to, in there, alternate interior angles. And so the full theta would be this 40 plus this 90. And so 40 plus this 90 equals 130. So either way you want to kind of solve, and I should have put here number 1A, we're going to get 130. Now, the harder one would be B, and so you can see we have the light coming in and bending towards the normal, and then as the problem says, it hits at the critical angle. And so this ray comes in from the air, it hits this glass block, all the angles are 90 degrees, and so that's going to become important here. I'll just kind of put it in my diagram. And so there's 90 degrees. It enters at this face AB, enters at 70 degrees, hits the top face BC, and then the key here is it hits it at the critical angle. So if I look at this first surface coming in and apply Snell's law, which is, N1 sine theta 1 is equal to N2 sine theta 2. It's coming in from air, so the index is 1, and clearly it's at 70 degrees. It goes into the glass block, let me just call that N, and comes out at some angle that would be right in here. Okay. Now, I could label it, and I better not use theta, because theta is here, maybe as a phi or an alpha or something like that. But perhaps since the goal of the problem is to find the theta, the critical angle, maybe I should just think of this angle in terms of theta, because what I have here is a right angle triangle, so that these two angles add to 90. All right, so maybe I'll just write this angle here as 90 minus theta. And I like that because 90 is a complementary angle, so I can write this as n cosine theta. And so this is the equation I get from the first step, where the light enters the glass block. Okay, so now as it zips across here, it's going to hit another interface. And so maybe over here I'll make Snell's law again, N1 sine theta 1 equals N2 sine theta 2. But this time we're in the glass, so the N1 is the index of the glass. And now the incident angle is that critical angle, theta. And then as it comes out, and this is kind of the key to the critical angle, it goes into air. And the critical angle occurs when the refracted light comes out and then bends 90 degrees. And so we've got sine of 90 degrees, which is 1. And so we have 1 times 1, which is 1. And so now we have our second equation. So you can see we have two equations that have the two unknowns, the n and the theta. So we could solve for both, although, and maybe I will, we didn't have to. The problem said just solve for the critical angle. So solving for the critical angle, maybe I'll use this equation to solve for n. And so I'll go sine of 7 degrees and divide it by cosine of critical angle and put it into this one. So this will be sine of 70 degrees over cosine theta, and then times that sine theta equals 1. And then the sine theta over cosine theta, I'll replace with tangent theta. And then I'll even move the sine to the other side. And now I can solve for my critical angle. And I suppose it doesn't matter if I'm in radians or degrees, but for problems like this, I like degrees. So I'm going to switch my calculator over to degrees and then go 1 divided by sine of 70, and then go inverse tangent of that answer, and get a critical angle of 46.8 degrees. Yay! And just out of curiosity, maybe I'll use that here to come back and find n. And so n would be sine of 70 divided by cosine of the critical angle, which would be, in my case, last answer. And it looks like the index would work if this was about a 1.37 indice for the glass block. But I won't put a box around it since I wasn't required to solve for it. All right, so law of reflection, Snell's law, right out of chapter 35, geometry and trig, and hopefully that went well for you. Let's move on then to question number 2. All right, so question 2 says, to display a small and 7.5 millimeter tall object to an audience, a scientist uses a lens and projects the images up on a screen. All right, now that's an important clue, and it's what I thought I would help you. If you're going to see something on the screen, that means the light has to really be there. It has to be projected on the screen. And so, hint, the light is projected onto a screen, and this tells you if the image is real or if it is virtual. And so it has to be real. It's on a screen. It's like the lab we did. The lab was entitled Real Images, purposely, because everything we did, we projected it onto the screen. And that's important too, because that means Q is always going to be greater than 0. Okay. And, well, there's some more I could say, but let's get to where we're going to need it here. All right. The image is 1.3 meters tall. The images. The object is 1.1 meters from the screen. What is the focal length? All right. Well, my first thoughts here are to do this 1 over P plus 1 over Q is equal to 1 over F. And they did tell me how far, let's see, what's somewhere here. The object is, so P is, and I'm going to put it in meters, 0.015 meters. Sadly, though, they did not tell me Q directly. But the other important equation is that the magnification, which is minus Q over P, which is also equal to the height of the image over the height of the object. Okay. So I could then, if I know the object height, the image height, and the object position, which I do, then I can find Q. And I'll put all that in there. So minus Q equals, and so P is the 0.015 that I mentioned. Here is where we're going to have to be really careful, because this is where it comes, Q is greater than 0. And you can see here, if Q is greater than 0, with P greater than 0, the magnification should be a negative number. In fact, maybe you remember that for us to get something bigger and real, we have to place the object just beyond the focal length. Okay? And what will happen is it will make a ginormous, real, inverted image. So they just tell us that the image is 1.3 meters tall. But what they don't do, hang on just a second. All right, head back. All right, what they don't do here is, directly tell us that it's inverted. And so that is kind of a clue. In fact, if you ever looked at something being projected on a screen, like an old movie, you always put it in actually upside down, and then it inverts it so that it's right side up on the screen. And to get your big magnification, if you remember working with these, it's just beyond the focal length. So all of that tells me, especially that last statement, that when they ask for, where'd it go here? Yeah, what is the focal length? It's probably got to be a hair under 1.5 centimeters, because we're going to get it really close. That's how we're going to get this big magnification. Okay? Because again, the size of the original object is pretty small. It's only 7.5 millimeters. And we're going to make it 1.3 millimeters tall. My point is that you might overlook this negative. Although if you do, then you're going to come up with a negative Q. And hopefully that will bother you. And you'll kind of pause and say, I can't have a negative Q. It's a real image. So that was kind of this hint that hopefully you won't go too far with a negative Q. Because I could see you just going 1.3 for its height and divide it by that and get a positive magnification, which, as I said, the math works out to a negative Q. But we need that negative for that to cancel off and get our positive Q. All right, so what is the Q? And so looking at this math, why don't I just cancel off the two positives, and I'll do the magnification. So 1.3 divided by 0.0075. So there's the magnification. Yeah, 173 times bigger. Of course, then multiplied by the P gives me 2.6 meters. So all of this should be done so that the screen is 2.6 meters away from the lens. And of course, now that we have the Q and the P, we can solve for the F. And so there's the P, there's the Q, and we will get our F. And of course, we will get a positive F. You can see that in the math. But again, it was the positive one that made things bigger and real. So again, if we didn't get a positive F, we should be bothered. So as we mentioned a moment ago, we should get a positive F, and we should get an F that is a little bit smaller than the object distance. And so maybe instead of 1.5 centimeters, I don't know, maybe 1.4, 1.3. Got to be real close to get a magnification of 173. All right, so let's see what we get. So this first one is 0.015, the reciprocal of that, added to 2.6, reciprocal of that. I'll hit equals, that equals the reciprocal of F, so take the reciprocal, and sure enough, we are at 0.0149. Wow. Okay, see, really, really, really close. We're only 1 millimeter further from the focal point. Okay, and so that's how we get the big magnifications. All right. Well, there's A. Let me switch to a piece of paper here for B. B goes on to say, now we have a bigger audience. And so for a bigger audience, which is a bigger lecture hall, we're probably going to need a bigger image. So we take our configuration and we add a new lens to it. And so maybe kind of drawing what we have already. Here's the focal length from the first one. We put our small object maybe upside down, and we get this giant image, which again we just calculated was 2.6 meters away. Now, for the bigger audience, we put a second lens that is only 10 centimeters from the first lens to make the image even taller. Now we want to get it bigger at 3 meters. So we're going to put a lens 10 centimeters away. And of course, I guess my focal length, which is only 1.49 centimeters, is not really drawn to scale compared to how far this is. But let me just put a dotted line to kind of represent a spot where we're going to put this second lens. Okay. And I guess I will start off by saying that the lesson that hopefully you learned is that the image of the first, so this one, becomes the object for the second. So in my mind, this distance here being 0.1, I would then have an object distance, you might even call it P2 for the second lens, as this 2.6 minus a 0.1, because the object for lens number 2 is this image from lens number 1, and its distance is 0.1 meters less than the 2.6. So this is going to be a 2.5. But then here's that hard one. This is that virtual object. And so my object distance is negative. Now, that's crucial because the first part of this question says, what type of lens are we going to use? And so without this lens, remember the light was coming together and focused at this point. To make it bigger, we want to actually kind of spread out the light. So the light was coming together and hit here. If we would put something here that would kind of spread the light, now not completely spread it out, otherwise it would never come together and focus. But given that this first lens is bringing the light together at this point, if we would put something that would, hinder the coming together, so a diverging lens, it may not come together till further out and therefore get bigger. And this is exactly what we did in the lab. Again, that real image lab. This would be the third double lens lab. And so this is a mimic of that. So all of that is to say that if I'm going to be answering B, part I guess, this would be the concave lens. I suppose another way of answering that is to remember that the magnification is minus a Q over a P. And like we did in part A, we know that the Q has to be real to be projected on the screen. And in this case, the P is a negative. And so that means our magnification has a negative on the top and a negative in the bottom, and so it is greater than 0. And it's going to make it bigger, so it's even going to be greater than 1 in terms of magnitude. But the fact that it's greater than 0 tells me it gets bigger. And that right there, like I said, is, what happens with this diverging lens. Or maybe put another way, it's going to be way out here. So when I go 1 over P plus 1 over Q and get a 1 over F, my Q is going to be positive and a bigger number than my P is negative. And since we're talking about reciprocals, this overall will come out to be negative. And so F will be less than 0, again pointing to the concave. And so hopefully you recognize that right away. If you don't, that's fine. But you will do the math here in a second. So let me go part 2 here where it says then, okay, what should be the focal length of this lens? And so if you don't recognize that it has to be a concave lens or a diverging lens right away, that's fine. But this will definitely give it away. That's the benefit of these pluses and minuses in this rule convention or sign convention. They're a pain to memorize, but remember they have those 2 advantages I talked about. The 2 advantages, this equation works in all cases, mirrors and lenses, all the mirrors and all the different lenses. And the other thing, it tells you some information about the P's and the Q's being positive. I've already been using that information about the P being greater than 0, and now I'm going to use that information to say if F comes out to be less than 0, I know it's concave. Well, let's just put in our numbers. So we already said P for this second one is a negative 2.5. What we haven't done is solve for the Q. But again, magnification minus Q over P, which again is height of object over, height of image over height of object. We can begin to calculate it. So I'll leave the minus Q, but just like in A, we know these other pieces. So I'm going to take the negative 2.5 for the P, for the second lens, and this would be the image of the second lens, and that's what we're projecting up on the screen. And so maybe that's a hard part of this problem too. This is a pretty hard problem. But we're going to just say that this is a 3. That's how big it is. Now, the height of the object, don't go all the way back to the original object. That is not really what we want. What we want then is to say, for the second lens, the object for the second lens is the image for the first. So our object for the second one is the height of the image from the first, and we were told that at 1.3 meters, 1.3 meters. And again, we want this to be positive, and that's good, see, because then we're going to get a negative over a negative, and we're going to get Q as a positive number, and again, further out than 2.5 meters. And so I'll just do the magnification out of curiosity. And the second lens only magnifies it about 2.3. And that makes sense. We're only making it bigger. I mean, like I said, the first lens made it the big size of 1.3, and then we're going to make it a little bigger to get to 3 meters. And then this times 2.5 right here. And so here we're going to need a further distance to the screen. And that's, again, like I've been saying, and totally makes sense because we're in this big lecture hall. We're going to want a bigger image, and we're going to want then a bigger distance to the screen. And now we can solve for F. And so this would be the negative 2.5 reciprocal plus this last answer, reciprocal. That's the reciprocal of F. Take the reciprocal again. And we're looking here at a negative 4.41 meters. Yay! All right, and then there's that negative. So if you didn't realize back here that we want this concave lens or diverging lens, we got it right here. So this would point back to that. So good problem, hard problem. Hope you did well on this one. I will tell you, maybe even surprisingly, you'll see that this kind of makes up for number 5. Number 5 is pretty straightforward, I noticed. So nothing like this one here. All right, so on to problem number 3. Okay, so number 3 says light with a wavelength of passes through a single slit. The distance to the screen is A. Find the, if the center of the intensity, the center has this intensity, 125 watts per square meter. What is the intensity 1.9 centimeters from the center? Well, this is hopefully kind of a straight plug and chug. It does involve chapter 38 with this really complex looking equation. And this is that sinc function. And so we need to then calculate it. And all this numbers are straight given. So this really is plug and chug here. But it's got a lot of parameters. And maybe I'll start with this. Why don't we just go, what is pi times A over lambda? And in place of sine theta, let me put the small angle approximation. So let's just do this number that goes into the sine function. And it's also the same number down there. And I'll just kind of calculate that one separately. And so these numbers are just, straight up given in the problem. And so I guess the first thing is the pi times the A, which is the opening, so single slit, which is 12 microns. The Y is the distance from the center. Let me change that to meters. Then we'll divide it by the wavelength, 652 nanometers. And we're also dividing it by the distance to the screen. Who knows what those each mean. So it looks like I get about a 0.845. And I should be very careful here, easy mistake to make, and ask myself, what are the units here? Are these in radians or in degrees? And so here I have a meter and a meter and a meter and a meter, and so no units. So those are real numbers. No units mean radians. That's why we call these real numbers here. So this must be in radians, because I want to do then the sine of that and square it. And if you remember, way back in number 1, we switched the calculator into degrees mode. And so now I better make sure I go back into my radians. So here I can go sine of that last answer. Why don't I just do this? I won't square it quite yet. And then I'll just also divide it by that last answer. And then hit enter. And then I'll do the square. And so I'll just treat those as a kind of a sine x over an x whole quantity squared. Okay. And then times the intensity at the center, which they tell me is 125. And so if I've done all my math here correctly, I get an intensity of 97 0.9 watts. So there's a lot to plug and chug, but it really is a straightforward plug and chug. All right. Well, now, something a little bit different. Let's look at B here. It says, now if the slit is being closed, and they give us the rate, the diffracted light spreads out. Now, I guess they don't need to tell me that the diffracted light spreads out. But if you remember, the diffracted light has this pattern here, which we called a sinc squared function, where this is kind of that spread. So we had this opening and the light came in and spread out. Okay. And so this is that spread, if you will. And so there's a angle of theta here and an angle of theta there. And so you might say that the angular spread is 2 theta. And this is the first dark spot. So in other words, this pi a sine theta over lambda is when the sine function equals 0, where theta is this, angle to the left or to the right. And of course, what that meant is this is kind of the angle to the left or to the right of where the diffraction is. And of course, we had the equation with an m here, because there would be a lot of places where the intensity is 0. But the main one is right here, because that's where most of the energy is all concentrated. It's even hard to see all these, as I was trying to demonstrate in the lecture here. So really what I'm just doing is taking this equation for diffraction and setting the m equal to a 1. And I'll even go one step further and do a small angle approximation. And so this is the connection between the angle and the A and the lambda. In fact, you probably recognize this then as the Rayleigh criterion, where, okay, when does the light, lose resolution? I'm going to write it this way, though, because where this gets hard, and I guess I got started on this when it said here it spreads out, you can kind of see then if A were to get smaller, the angle theta has to get bigger, because the product of the two always has to be the wavelength. Now, that'd be a constant for a given, beam of light coming through here. And so that's the mathematical answer to this phrase. If the slit is being closed at a rate of 10 micrometers per second, the diffracting light is spread out. Yeah, of course, because this is the connection. And so you didn't have to do all this math, here, but I do hope that you would have maybe started here at saying A sine theta equals lambda, or maybe even started here. Okay. But here's where we get to the heart of the question. It says, at what angular rate is the light being spread when the slit is now closed to 9? So it's slowly closing. Let's see, what do? We start at 12, and it gets smaller and smaller. And at some point, it is closed up to a 9, and it's closing at a constant rate. And the hint I tried to give you here is, remember, if you know anything about positions, you also know about rates, velocities, accelerations, by taking the derivative. And so I would say this equation has to do with position. So if I were to take its derivative with respect to time, I would get an equation connected to its rate. And the A is changing, and as it changes, the angle changes, but the wavelength does not. So taking a derivative is a product rule. We've got the first times the derivative of the second plus the second times the derivative of the first. Now, the other side of the equation, I would take a derivative of a constant, and that's just a 0. And this is perfect because they give me some information. First of all, they say when the slit is at 9 micrometers. So right there, I have 9 micrometers. Now, I would also argue that back here, if we know the A, we also know the theta. All right, so the theta, which is the wavelength divided by A, and so that's going to be this term here. So I have enough information to get the A and the theta at that particular moment. So this is the, what was it, 652 nanometers divided by the A, which is the 9 micrometers. All right, so 652 nano divided by 9 micro. And so the angle, and this would be a real number, right, because this is a distance over a distance, so this is in radians, would be 0.07244 repeating. Now, these other two, this one right here says, how does A change with time? Well, that is really what this phrase means. The slit is closing. This is the rate at which it is changing. And so just changing these words to an equation, that's what those words say. So my dA dt is 10 micrometers per second. Ooh, don't miss this. Negative. It's closing up, right? The A is getting smaller. And so the rate of change is a negative number. It's going, from 12 down to 11, down to 10, down to 9. It's a decrease. So read your math carefully here. And then, of course, the thing we don't know is exactly what we're looking for, the rate at which this thing spreads out. Although we're going to have to double it because the spread angle is times 2, but at least we're going to find the d theta dt, okay? So putting all this together, this would be the A, 9 times 10 to the minus 6. And then here is the d theta dt I'd like to solve for. Okay, plus the angle, 0.0724 repeating, times the rate at which A is changing. That's a negative 10 micrometers per second. Okay, and maybe I should have put meters here. So, of course, meters is going to cancel out, and that's going to be a 0. And so the d theta dt comes out to be, all right, actually that's already in my calculator. So I will go times, and I'm going to imagine bringing it to the other side. So I will just ignore the negative because that's going to change when I bring it to the other side. So that's 10 times 10 to the negative 6. Okay. And then once I bring that to the other side, I will be dividing by 9 times 10 to the negative 6. And so if I've done all this correctly, it looks like I get an 805 with a 0 in front. And of course, that would be radians per second. And so the whole beam at twice that would be times 2. And so this is my kind of my relative rates equation. Yay! And so there's actually another pretty hard one. Hopefully not too hard, but much, much harder than the A was. We just kind of plugged and chug into the single slit. Okay, let's go on then to number 4. And so number 4 says what? So here it says an engineer is building a reflecting telescope to observe the warm hydrogen gas. So hydrogen gives off this particular wavelength. So astronomers are designing their telescopes a lot of times to zero in on this, to maximize. So we want a lot of light, the light that's reflected. And so what we're going to do is we're going to make this thin coat here on the glass. So here's the glass, and it comes in from the air, so the index is 1. And a thin film has an index of 1.25. And if you remember our discussion on this, then there's going to be a phase shift off the top surface of the thin film as well as here. And this is that long discussion, and maybe you saw that video I put together to help you decide, do you use 2Tm equal an integer number of wavelengths or 2Tm plus a half? And it's not so easy because it depends. Are you looking at reflected light or transmitted light? Are there 0 phase changes, 1 phase change, or 2 phase changes? And are you looking for a lot of light or a little bit of light? So I think we can answer that. Number 1, we want reflected light. Number 2, there are 2 phase changes. And number 3, we want to maximize it, so we want bright. And I made that little video, and I kept my little chart here so that we could go through those questions about, you know, if, and if, which one to use. And so the first one is, I'd say, we want reflected light. So we can ignore these 4 options. The other thing is we have 2 phase changes, so we can be in this column. And then the last thing is we want bright. And so for this one, we're going to want this equation. Now, as long as I'm tackling this problem, why don't I also then mention B? Because in B, it says if we use a different material. Okay, so now we'll have the light coming in from the atmosphere. We're going to put a thin coat on our glass surface. And then that coating has an index of 1.62. And in that case, when the light bounces off and then bounces off, we will get a phase change here, but not here. And so that's going to change our thinking in this little chart. In this case, we still want reflected light, okay. And now we're kind of in this column because we only have 1 phase shift. And of course, we still want to make it bright. I mean, we're, building a telescope so we can observe the outside world, so we want it bright. And in that case, we would use the equation 2T equals m plus a half lambda naught. And so we're going to mix our equations. We're still trying to get the maximum, but because of the index and the number of phase changes, we have a different criteria to meet. So coming back up here to A to do our calculation, the minimum thickness, or what is the minimum thickness, we can set m equal to 1. And so we would have lambda naught divided by this 2, and then also this index. In other words, it's a half a wavelength in the material itself. So the wavelength is 656, and I'll just leave it in units of nanometers. then I will divide it by 2, and I will divide it by the 1.25. So we would want to build a little thin film that is 262 nanometers thick. Whereas in part B, we would have a thickness of, and so now you can see where it switches. Again, I'll just do m equals to 0, but now I have a quarter of a wavelength in the film. And it kind of makes sense because a quarter means down and back would be a half wavelength. And the half wavelength is equivalent to a half a phase change, and that one has also a phase change, and then they match up again. Whereas this one, they both underwent a phase change, so we can really ignore any phase change. And then this one goes down and back, so we need a half a wavelength down and a half a wavelength back up, so the difference is 1 wavelength. So this is why it's half a wavelength in the material, and this one here is a quarter of a wavelength in the material. And the material actually has a higher index. So this thin film is going to be a lot thinner. Not only do we have a factor of 4 in the bottom instead of 2, we also have a higher index. And so for both of those reasons, we expect a smaller film thickness. In fact, maybe too small to engineer well. But let's see what it comes out to be. 656 divided by 4, and then divided by the index of 1.62 is what I wrote down. Yeah. And so we're looking at about 101 nanometers. Well, that's not bad. Both of these are relatively easy to do. So, nice. All right. Oh, good. Finally, a much shorter one compared to number 2 and number 3. So, good. Glad that one, and hope it worked out well for you. All right. Let me then look at the last one, number 5 here. And number 5 has a Young's double slit experiment, which says d sine theta equals an integer number of wavelengths. All right, so on this one, let's see, in a Young's double slit experiment, the two slits, light of wavelength 632, has its third order, okay? And so maybe if there's anything kind of tricky here, it's to make sure that the third order bright fringe means m equals 3 here. And the wavelength is 632 nanometers. On this side of the equation, there's the D, and that's what question A is asking for. What is the spacing between the two slits? So we're solving for D. And again, we can do the small angle approximation, which is the y over L. And so the L is right here. The screen is 2.35 meters away. And this third order bright fringe, and that's in centimeters, so I'll convert it into meters, will allow us to directly calculate D from this. And so this one, like I said, is plug and chug, but it is a little hard to remember then what each of these, words mean. And so that's probably the challenging one on this one. So if you know what each of those means, this one hopefully went pretty straightforward. So 3 times 632 times 10 to the minus 9 nanometers. Maybe I'll just imagine bringing this over 2.35 and then imagine bringing this to the other side, 0.0456. And I get a D value of 9.77 times 10 to the minus 5 meters. And maybe that's just as good. I don't know if 97.7 micrometers is much value added to that. But that would be the spacing in our diffraction gradient. Okay. And then B, just says, now, what wavelength of light would you use if the fourth order then were to be at this same position? So maybe you shine both colors and they overlap, or maybe you just turn off this one and go to a new wavelength, but it's still going to be AD sine theta equals 2m lambda. And that's what I wanted you to recognize. Nothing really changes. We can even do the same small angle approximation. Although the one thing that is crucial here is we're saying now we're at order 4. And since we're using the same diffraction gradient, this d is that same value. It's something physical in the gradient that doesn't change. So this is the 9.77 times 10 to the negative 5. This right here is that same y, 0.0456 meters. The L is the same, 2.35. Then we get a 4, and we get a lambda. And so that number already being in my calculator, and then dividing it by that, and then finally imagine bringing the 4 to the other side and dividing. We get 4.74 times 10 to the minus 7. I kind of like to write it as 474, and that would be 10 to the minus 9, so nanometers. And that way I can see where it is on the visible spectrum. And so it is in the visible spectrum, and it's maybe towards the bluish, or definitely blue. Maybe, yeah, blue. Let's see, what is Roy G. Biv, but indigo, blue, probably closer to blue and indigo, but not quite in the green. Anyways, color doesn't really matter. There is the wavelength. Okay, that's it. Hope it went well for you. And looks like there were some pretty challenging ones in 2 and 3, but hopefully pretty straightforward in 3 and 4, and even 1. Had a lot of trig and geometry in it, but relatively straightforward. Okay, well, hope you learned a lot. If you made any mistakes, take care.